So, which branches and jumps would this data path here support? Well, first thing to look at is which do we have paths for the next PC. So here's our PC, and the next PC is going to come around this way. So what are the possible values that we can have coming this way? Well, if you look over here, there's a mux, and the mux has two inputs. So we've got one of them here, which is this one coming through here. And what's this? Well, this is PC plus 4. You can see we take the PC, we add 4 to it, and that's one of the options. And what's the other option for the mux? Well, the other option for the mux here goes through the adder, through the shifter, through the sign extender, and back to the instruction. So this is our PC plus 4 plus the immediate shifted by 2. This is how we generate the address for a conditional branch. Okay, so in this data path, those are the only two paths we have. So which of these from the list can we eliminate? Well, all of these ones here, we don't have any paths to provide the addresses for these ones. Okay, so now which is this? Is branch equal or branch not equal? To see that, let's take a look at what condition we're calculating. So over here we have an AND gate, and we're calculating the AND of two things. We're calculating the AND of if it's a branch and if it's 0. So this is 0 and branch, and this is the condition for branch equal. We know that they're equal because it's 0 and we have a branch instruction. So in this case, it's not branch not equal, so this is a data path for doing just branch equal. Let's look at a practice for this. How can we go about adding unconditional jumps to this data path? And so to get started, start out with two things. What do you need, and where are you going to get it from? So to help you out, here are details about the addresses and the formats for these two instructions. You can see the branch equal not equal format has a 16-bit immediate, and the jump format has a 26-bit immediate. You can see where the input is stored, and you can see how we use the addresses. So remember, when we're doing this conditional jump, we're going to take the current PC, add 4, take our shifted immediate, and add it in. But when we're doing a jump instruction, we take our 32-bit PC, and we add in the whole value here for the immediate. We just overwrite it. So we're just replacing whatever we had for those bits with the immediate value. So what do you need, and where does it come from? Well, to do this, we need the address for the jump. So we're going to add an unconditional jump, a J instruction, so we need the address. We need a control signal, which tells us to choose that. So over here we've got a mux. Remember, this was for branch equal or no branch. We're going to need to make this mux bigger so that we can have the other jump too. And we need that mux to choose it. So we either make the mux bigger or add in another mux. Now, where did these things come from? Well, the address is going to come from the instruction. Remember, we looked at the encoding. Those bits are in the instruction bits. And the control signal to control this new mux we need, well, it's going to come from our control logic. So we're going to have to extend that. So now you're ready for part 2. Go ahead and figure out what you need to change in the data path to be able to support that. You're going to need to add some wires, some logic, some mux, and some control. All right, so here's our new data path, and let's take a look at what we added. Here are instructions, and remember, we're going to do a J format instruction here. We've got an opcode and a large target address. So for the wire, we need to get the address bits from the instruction bit. So here's our instruction. We have to add a wire, which takes some of the instruction bits. You can see it's 25 to 0. It's 26 bits. Here's our 26 bits down here. We're going to take those out. We have to add some logic. We need to shift it left by 2. We need to add a mux. The mux here is going to let us choose between our previous conditions, which were branch equal or no branch. And we're going to have some control logic so that we can control that mux. So we have a control here, and we have to add another wire which tells us whether or not we're doing a jump instruction. Now if you notice here, our control has two outputs, a jump and a branch. So this data path can do jump and branch instructions. Now how does the control logic work? Well, it just looks at the opcode of the instruction. And if the instruction opcode is a jump, then it will go ahead and tell the mux over here to take the jump address. How about adding conditional jumps? So what do we need to do to a conditional jump? What's the ALU going to do? What mux logic do we need, and what control logic do we need? All right, so here's our ALU, and what's our ALU going to do? Well, it's going to do subtraction, and that's because we want to know if we're going to do a conditional jump. So 0 tells us whether their two registers are equal. So if we want to do branch equal or not equal, we need to take the 0 output here. I'm going to send that into our mux logic. All right, what does the mux logic need to do? Well, the mux logic needs to handle two conditions. One is, should we do a branch equal? One, should we do a branch equal and a branch not equal? And it has to do the right thing depending on the 0 output. So if the 0 output is true, that means they're equal. So if we're doing a branch equal and it's 0, we want to jump. Or if we're doing a branch not equal and it's not true, we want to jump. So we need two different conditions for branch equal and branch not equal. And that's what this logic looks like. So If it's not 0 and we have a branch not equal, that means they're not equal and we want a branch if not equal. Or if it is 0 and we have a branch equal instruction. This is it is equal and we want to branch on an equal. So that's going to be the logic in that mux circuit there. Now our control over here is going to have to do something. It's going to have to send these signals over here. So we actually need two outputs here. Because if you look at our mux logic, we have branch not equal and a branch equal going into it. So we're going to have two outputs here. We're going to have to have one for branch not equal, one for branch equal. That combined with the 0 here allows us to do the mux logic.